Okay. So we looked at theorem 12, right? So theorem 12 was basically saying that it was reminding us, right, that there is a very strong mapping between the set of linear operators from V to W. Let me change. The set of linear operators from V to W to the set of all M cross N matrices. Right? This was theorem 12. Okay. So the statement was that this is an isomorphism. And now what we're going to do is we're going to continue from there. Right. So this is the theorem statement that we just saw. Right. Theorem 12. The proof we already saw in one of the previous lectures. So now we're going to continue with an example. Okay, so let's look at example 14, right? Just to get a hang of how the matrix is given for a linear operator. So suppose F is some field, right, and T is some linear operator, which is defined as follows. Okay, so it's basically removing the second component. Okay, that's just the definition of the linear operator. It is easy to see that this is indeed a linear operator. Give me a second. So it's easy to see that it is indeed a linear operator, right? This is completely trivial. Okay. So now what we're going to do is we're going to consider one fixed basis. So the basis is just the standard basis, 1, 0, 0, 1. Right? So this is E1, and this is E2. Right? That's the standard basis. What we're going to do is, so what we want to do here is we want to write down the matrix. So remember, for every linear transformation T, one can associate a matrix A with it. Okay? So that's what we're going to try to do now. Explicitly. So the way we do it is we apply T to the element of the basis B. So T of 1, 0 is going to be what? So you just keep the first component, right? So T of 1, 0 should be what? Yeah, exactly. It stays unchanged because the second component is already 0, right? Okay. So this one can write as a linear combination. So it's 1 times epsilon 1 plus 0 times epsilon 2. This fine? Yeah. Okay. And then T of epsilon 2 would be what? T acting on 0, 1. What would this be? Right? We're just removing the second component. So this is 0, epsilon 0, 3. Okay. And now the matrix, remember, so the way we had defined the matrix for T was, does somebody want to remind me? So suppose the basis was alpha 1 to alpha n. Okay, so suppose this is the basis. Then how did we define the matrix? We said T of alpha j is going to be what? So I forget ij, it's probably ji. No, it's ij, I think. Alpha. Okay. Right? This was just the definition. Okay. And now these, and this is what the matrix was, right? So now what we have done is we have written T of alpha j. So we have written T of alpha 1 as a linear combination of alpha 1. So we've written as T alpha 1 plus 0 alpha 2. And T alpha 2 we've written as 0 alpha 1 plus 0 alpha 2, right? So now you can read off the coefficients of the matrix, right? And so you can write the matrix. Any questions about this part? Is it okay? All right. Okay. So now let's look at, so this was a relatively straightforward example, right? So let's look at a slightly more interesting example now. So example 15 is the following. It says, so let V be the space of all polynomial functions from capital R to capital R of this form. Okay, so it's basically saying it's a degree 3 polynomial. Okay, so you're going to look at the space of degree 3 polynomials. That is the definition of V. And you're going to consider the differentiation operator that we did in example 2. Okay. And is it clear that this differentiation operator is going to map V to V? Right? Why is that? Right, so differentiation can only decrease the degree, right? So if it's at most degree 3, it can only decrease it. So this is fine. Okay. Now let B be the order basis of V consisting of the following 4 functions. Right? So we have to choose a basis for the space of polynomials of degree 3. How do we do this? So it's just saying that you take it to be the polynomial. So F0 is basically, sorry, it doesn't start with 0, is it? So F1 is just the constant. So it's 1. F2 is, what is F2? You have the definition here. Exactly. F2 is x, right? F3 is x squared and F4 is x cubed. Is that okay? Just the definition. Okay. Now what we want to do is, so we're going to apply the same procedure, right? So the procedure was that you apply T alpha j. So you apply on alpha j the operator T, and you write it as a linear combination of alphas, right? So alpha here is just the basis. So we're going to basically write it down. So df1, the differentiation of f1, what is that? Right? Differentiation of f2 is, right? Is this okay? Is it making sense? Yeah, okay. And so on, right? And now one can express the whole thing because we know that f1 is by itself 1, f2 is x, f3 is x squared, and so on. One can essentially express all of these as linear combinations of f's. This is fine. So the first one is 0, so all coefficients are 0. The next one is x, so it's so the next one is constant, so it's 1 times f1. Third is 2 times x, so it's 2 times f2, and so on. Is this okay? Making sense? All right. So now one can read the D matrix. One can read the matrix Aij, right? This matrix here. So one can read it. Remember, this was the notation we were following. That so here T was actually D. So D of beta is just the matrix A, right? Essentially. So the matrix A is exactly this object. Is this clear? Oh, it's just, it depends on your convention. We are writing it as AJI. If had you written it as AIJ, it would be the other way. Just rows and columns, right? That's all that's getting to. Yeah, it's this one, right? It's this one. This one, it's that one. Yeah, that's what I'm saying. It depends on your convention. So because we defined it to be AJI, that is why it's turning out like this. Had you defined it to be AIJ, it would be the other way. But then you would have to do row multiplication instead of column multiplication. You just have to be consistent, that's all. Okay. The reason is, yeah, so you have dB, right? And then when you have a vector, say alpha in B, then this would be a column. And this matrix is defined such that it's just column multiplication would give you, the result in as a column as well. It's just consistency. Yeah. Okay. All right. So let's continue then. So yeah. So that was the entire example, right? So this was basically showing you how you can write it in this space. Uh-huh. It's just saying that the action on the first vector is the zero vector. That's all it's saying. Any other questions for the example? All right. So let's continue then. Right. So now, okay. So we have seen what happens to representing matrices when transformations are added. That is, the matrices add. Right. So we saw that if you have T plus U, right, this was defined, as the linear combination of these linear operators. So it's just the sum of the linear operators. Then the matrices also add. Okay, this we already sort of saw. So suppose it's a T beta plus U beta. Okay, so that's the statement, right? So the representation of T plus U is the same as the representation of T plus representation of U. Now, what we're asking is what happens when you compose transformations. Okay, so now, as usual, we take three vector spaces, V, W, Z. T is going from V to W, and U is going from W to Z. Okay, and we have ordered bases for each of the spaces, right? So this is for V, this one is for W, and this one is for Z. Okay, so we have three bases for the three different spaces. And now we are saying, suppose A is the matrix for this pair relative to BB prime. So the matrix for T relative to BB prime is A. Okay, and then the matrix for U relative to B prime, B double prime is B. Okay, it is easy to see. Okay, this is so the assertion here is the matrix C, so UT in B double prime is basically just A times B. Or sorry, B times N. It's not commutative, so okay, is the claim clear? Yeah, so the matrix relative, these are relative to the basis, right? So we had defined it as follows. So we had said that T, it's exactly the same definition. So T alpha J is the same as sum over Ji, and then you can put beta J or beta I, sorry, sum over it. Okay, so alpha is say the basis for B. This is B prime. Okay, so this is alpha 1 to alpha m. This is say beta 1 to beta. Okay, so this matrix is what is the matrix. So this is what I mean by T. Is that clear? Any other questions? Is it clear? All right. So right. So the assertion is clear, right? That so if you have the matrix for T, the matrix for U, then the matrix for UT would be just VA. Okay, and you notice that obviously these things are changing. So it's from B to B double prime, right? Because UT is taking you from, yeah. So where is UT taking you from? V2. Which is Z, right? Because T is taking you from V to W, and then U is taking you from W to Z, right? So therefore, this basis is B, and this basis is B type. Is that okay? All right. So how do we see that this is actually the case? So let's go through it, right? So okay, so we have that T alpha of beta prime, or sorry, B prime is the same as A acting on alpha B. Is that okay? Because A, remember, was just P of B prime, right? That is essentially, yeah. So this part is fine. Okay. The next step is saying what? The next step is saying, okay, so let's apply it to U to T alpha. And when we do that, what we expected to get is the following. So we have B acting on T alpha, B prime. So this we just evaluated. And what was that? It was just A acting on. Oh, actually, yeah. So that's as far as it went. Okay. So this is fine. This is B is the representation of Q. Is that okay? So B was, what is B? B is just U acting on B prime to B double. So the representation of U relative to B prime. Is that okay? All right. And then finally, we can combine these. So therefore, we have UT acting on alpha with B double prime is going to be B, right? And then you substitute for T alpha using this equation, and you would get BA acting on alpha B. Oh, sorry, alpha B. Is this okay? It's very straightforward. Okay, there's nothing very complicated happening there. Okay, and then by the definition and uniqueness of the representing matrix, we have that C equals B. Right, so we're using uniqueness because there's no other matrix, right, that could possibly represent the same operator. This we proved already. So therefore, if you find one representation, that is the only representation. Yeah. Okay. So another way of seeing this is by direct computation. So this I will leave as an exercise. You can just directly apply the definition that I said right here. The definition that I found here. So one can use this definition directly, and you would get the answer. Okay, you just apply the definition repeatedly, and you will get the final form. So in the first case, you apply the definition of T alpha J in terms of Aij, and then you apply it to U beta K. For U, you know the definition in terms of Bij or Bik. And then you can basically combine the matrices to get gamma I, and then you can say Cij has to be exactly the subset. Is that okay? Any questions? Do you need a minute to resolve, to think? Can we move on? Yeah. Okay. So here what we are saying is that we're going to look at the definition, right? So T alpha j, right? This was what we said it was a j I. Let's say beta I, right? So we're just using the definition here. When you use the definition, you can express it as follows. Is that okay? All right. Now what we're going to do is we're going to say that this is just a scalar, right? So the scalar I can move. It's not a problem. It's a linear operator. So I take the scalar outside and then I'm multiplying u with beta k. And u with beta k, I will have again a similar thing. So u acting on beta k is the same as sum over a k, say L. I don't know what they're using, I. Okay, and then here we make it into, let's say gamma. So sorry, it's a different matrix. So let's call it B because we already used A for T. Let's call this one B. Okay, so when you make that substitution, you would get this object here. Correct. And now you just rearrange and you will have this final result. Right? And what does this look like? This just looks like matrix multiplication, right? Because you're doing BIK, AKJ, sum over K. This is exactly what B times A's IJ component looks like. Correct? Is that okay? And okay, and so that basically gives you the matrix C. Right? Because what is C? C is that UT acts on some vector, which is some linear combination of the final thing in terms of some coefficients. Is that okay? Any other questions? Okay, thank you. Yeah, it's good. Interrupt me, okay? If it's not clear, don't.
Like okay, like if the second step we say that it's the summation of a n beta, right? But like you say that you got the guidance from. So you can just differentiate it like a function of the summation like so if it is the function, so then sum function that's summation. And then that the function can also be equal to the summation that is in function.
The summation can also be taken as a? Yeah, that's linearity, right? That's what I said. You're using linearity. Otherwise, you cannot do this step, right? Yeah, exactly. Yeah, there's no interpretation. This is exactly what we're using. We're using the linearity property, right? Like to go from this step to this step, so from 1 to 2, you have to use linearity, right? Exactly. This is not true in general, right? Like, so if you just sum, this property is exactly relying on linearity. If you have gamma I, the fact that this is the same as Ci f of gamma I, right? This is using linearity. Yeah, so this is one way of proving it. You can also prove it the other way. So one way of proving it is to use the definition of, like use the intermediate objects. We defined all these objects already, so you can use those definitions. If you don't want to do that, you can also just plug in the, like you can just open everything and write it directly. So there are two ways of doing proof. Any other question? Okay, let's move on. Okay, all right. So recall that we had motivated the definition of matrix multiplication using operators on rows and columns of a matrix. Now you see a much stronger motivation because it shows you how linear transformations compose, right? So this is how we had defined matrix multiplications, right? But this was when we were studying, row operations and all these things. So it was in a very different context. Now it is showing you that this is actually very interesting because it shows you how linear operators compose. Okay, does that sound good? Okay. So let's continue then. Okay, so this brings us to theorem 13. So theorem 13 says the following. It says that let V, W, and Z be finite dimensional vector spaces over the field F. Okay, and T is basically just formally stating what we had. Okay, so T is going from V to W, U is going from W to Z. Okay, double prime are the basis for V, W, and Z. If A is the matrix for T relative to BB prime, and B is the matrix for U relative to BB prime. Okay. Then the composition of UT relative to B prime, B and B double prime is this differentiation. This is exactly what we just showed. Okay. Is the statement clear? Is the proof clear? So let's continue then. This I say I have to skip in the class. I'm going to skip it. We'll look at it later. Probably I myself didn't understand what is happening here. So okay, we can skip it for now. All right. Then there are a few notes. So the first note says that if T and U are linear operators on the same space V, we represent everything in the same ordered basis V. This we already mentioned, right? So because earlier T was going from U to V, we had a basis, so U to V. We had a basis B, B double, B prime, but it's saying when it's going from, say, V to V, V to V, then we use the same basis B, okay? And then the theorem can be written much more simply, right? Then you can say that the representation of the composition in basis B is the same as multiplication, matrix multiplication of the representing matrices for both of these in the same basis. Is that okay? It's a very simple statement. Okay. And in this case, the correspondence which B determines between operators and matrices is not only a vector space isomorphism, but also preserves products. Okay, so basically what this is saying is that so this mapping is not only an isomorphism, it is also preserving these products, right? Because UT, when you apply this operation, is going to U times T. Right? So it's preserving the product structure of the mapping. Is this clear? What is being said?
So it's not. So it's the same.
Yeah, but the bases were changing, right? So you it was not like one space. So the products were so UT. Yeah, so the bases are not changing, so you can define products much more cleanly, right? So the product of operator is going to be a linear operator in the same space. The order will matter. So TU would not be the same as UT. Of course, you're right in saying that in the previous thing, the other way is not even defined, right? Because if you're going from that is correct, but it doesn't mean that this would be true. Like it's matrices, right? Like matrices don't commute, so UT will not be same as TU. Any other questions? Okay, all right. So a simple consequence of this is that the linear operator T is invertible if and only if the matrix TB is invertible. Okay, so it's a consequence of preserving the product structure. Why is that? So let's take a look. So remember the definition of to define invertible matrices, we have the identity operator, right? And in any ordered basis, so we use I as the identity operator. And the definition of invertible was that there exists a matrix U such that UT is the same as TU is the same as identity. Right? This was the definition of for something to be invertible. Okay. Now, because this operation that maps linear operators to their corresponding matrices, right? Since this operation preserves inner products, I'm saying it preserves products, right? So that would mean that U times T is the same as T times U, I'm dropping the B, right, is the same as identity, right? So it's saying even at the level of matrices, the notion of having an inverse is exactly the same. Because remember, what was the definition of an invertible matrix? It was the same, right? It said that there has to exist some matrix such that when you multiply on the left or the right, you get identity. So it's basically preserving the definition because the product. Okay, so it's a very simple observation, but it seems to have this very nice consequence. That if T is invertible, that is equivalent to saying that the matrix that corresponds to T is invertible. Is that okay? Okay, let's move on. All right. Okay, so now we are looking at the next step. Okay, so let us now look at what happens to the representing matrices when the ordered basis is changed. Okay, so far we said that we'll fix one basis and we look at the matrix corresponding to it. Now we want to understand how this matrix changes if you change the representing basis. Is the question clear? Okay. All right. So for simplicity, we consider this question only for linear operators on space V, so that we can use a single ordered basis. So we're going to basically restrict to operators that map V to itself. Okay, so just as a reminder about notation, so linear transformations can normally go from V to W. Okay, but if W is the same as V, then we call them linear operators. Okay. It's just notation. So here we're going to focus on linear operators. So we don't have to worry about the fact that the dimension of the space is changing itself. Okay, so let's continue. So let T be a linear operator on the finite dimensional space V. Okay, so B is alpha 1 to alpha n, B prime is alpha 1 prime to alpha n prime. And suppose these are two ordered bases of V. This is fine. For the same vector space, we can have multiple bases. That's not a big problem. So the question is formally, how is TB and TB prime? How are these two matrices related? Okay, so we saw this in chapter 2 that there is a unique invertible n cross n matrix P such that a basis, so alpha, some vector in the basis B is going to be some invertible matrix P times that same vector in the basis B prime. Okay, this we saw in the previous chapter. Hey, this is just coming from linear independence and so on. Otherwise, something becomes linearly independent. You can't really shut it. Okay, so this we already saw in the previous chapter. Okay, so I think I messed up. Let me write it for here. So B alpha, B template. Okay, and in fact, this matrix we could actually write explicitly as follows. So this matrix was nothing but you're writing alpha 1 prime in the basis B, right? In the alpha basis. Okay, and then you write alpha 2 prime in the alpha basis itself. Okay, so this was exactly the structure of the basis. Is that okay? And the proof is also very simple, right? Because you just yeah, let me not do the proof. You just have to use the definition and expand it. Okay. So now by definition, T acting on alpha can be written as T times alpha in the corresponding matrices, right? This we just showed, so this is okay. And now if we apply 3, 7, this fact over here, we can transform alpha into T times, oh, sorry, let's see what that means. Okay, so you apply 3, 7 on the vector T alpha. Okay, so on this vector, we're going to apply this equation 3, 7. So T alpha of B would become P times T alpha in B prime. Right, so we just changed the basis from B to B prime. That's all we did. And we know we can do this using the operator P. Is that okay? Yeah, no? Okay, what is the question? Tell me. Where did you get stuck? This step is not clear. Equation 3, 9 is not clear. Okay. So what did we say? We said equation 3. This equation, right? This is 3, 7. So 3, 7 said what? It said that if I have two bases B and B prime, the same vector can be written in the B basis and the B prime basis by basically multiplying with T, this invertible matrix. This is fine. Okay. Now T alpha is a vector in the same space, and we have it in the basis B. How will I write it in the basis B prime? Exactly. So that's all that 3, 9 is doing. Okay. Is it clear? Okay. So that's all we did. All right. And now what we're going to do is we're going to combine these. So we're going to combine 3, 7, 3, 8, and 3, 9. Okay. So when we combine them, what we get is that yeah. So on the right hand side, we have so let's look at this equation. We substituted T alpha B with P times T alpha B prime. Is this step clear? So we just substituted this object over here with P of T alpha B prime. Okay, so that's the first part. Is this okay? Okay. And then what did we do in the next step? In the next step, we had t, which is as it is. So we left it unchanged. And now alpha, we are changing it again to b prime. Okay? By multiplying with p. Is that okay? So we get this equation then. And now in this equation, we are going to move p to the other side. So we have p inverse acting on tb and tb prime. And this will give you the representation of tb prime. Okay? And what this means is that it must be the case that t of b prime is the same as p inverse tb p. Yeah, because what is happening is we are saying that the action of t alpha b prime, right? This was supposed to be what? This was supposed to give you the yeah. So what we wanted was that there is some b prime, right? And we wanted some matrix here, right? And what is this matrix? Can you read from the expression? It is this part, right? Right. So correct. So what this is saying is that the representation of T alpha in the B prime basis is related to the representation in the B basis by this transformation. So, is that it? Yeah? Okay, and this is what is called a similarity transformation. So we'll define it in a moment more carefully. The similarity transformation is basically relating two matrices by P inverse, conjugating by P inverse. Okay. Got it. So that is basically the that part will come. Like, once we start doing vectors, I think it'll become much more clear. So we'll look at it. Yeah. So for now, we're just thinking of this as a change of basis. So similarity transformations are basically showing up when you're changing your basis from B to B. Okay. So we saw that for vectors, that you just have a multiplication with P, and for operators, you have P inverse multiplied with P. Yeah. Okay. Any other questions before we move on? It's all clear. Okay, so before stating this result formally, we observe the following. So there is a unique linear operator U that carries B to B prime defined by the following. Okay, so you have U mapping one basis to another. Okay, so why that is because if this was not the case, right, if you had two linear operators that are not the same, but they were mapping one basis to the other, then the linear independence will get in trouble. Because you can take the difference between U prime and you'll get vectors, linear combinations that are not exactly the same. Okay, so I can leave the proof as a homework case. Okay, so the claim is that there is a unique linear operator that would map basis of one to the other. I think these are also consequences of what we've already studied. Okay, and this operator U is invertible since it carries a basis for V into a basis for V. Okay, because if it was not invertible, then again you would have linear dependence. Right? Okay. Okay, so the matrix P above is precisely the matrix of the operator U in the ordered basis P. Okay, so we say that. So we had earlier stated this, right? We said that alpha j, we can write it as P times alpha prime j, right? This was a matrix. Right, if these are bases, we knew that these are related by this invertible matrix. Now what we're doing is we're using the language of operators. We're saying that U acting on alpha j gives you alpha j prime, and this U is unique if alpha j and alpha j prime are bases, right? And now we are asking, what is the matrix? What is the matrix corresponding to U? To U in the basis B. Okay, so this is B and this is B prime. Is it clear what is happening? So we first said that the two linearly independent bases sorry, the two bases are related by some invertible matrix P. Now we are saying that if you have two bases, then there has to exist some unique linear operator that maps one basis to the other, right? And now we're asking, well, what is the matrix representation of that matrix? Okay, obviously it has to have some relation with P, right? And it turns out that it's the same. Okay, so this is what we are showing. So it turns out that the matrix representation of this U is exactly P that we had to solve. So why is that? So let's see. So P was defined as follows, right? So P was defined as alpha j prime is some linear combination of alpha i's using the P's, right? And now since uj is the same as u alpha j is the same as u alpha j prime, one can rewrite this equation as follows. So you multiply uj, u of alpha j, okay? And here you get alpha j prime you substitute from the equation above, and you get this equation, right? And remember, what is the definition of the matrix for a linear operator? It's exactly this, right? That it maps u alpha j. The matrix representation is just sum over I. It has to be some matrix aj I alpha I, right? That is how we had defined the matrix for a linear operator. Correct. So now you can read it off, right? So the coefficient of alpha I gives you the matrix, and here it is giving you the matrix. Okay, so it's clear that A is the same as P. So this is what you get. So the matrix U is exactly the matrix representation of the operator U in the basis B. Is that okay? Yeah, so okay, so let's see. So now, okay, so suppose U was not invertible, right? You would sort of run into problems with okay, so let's see. I also don't fully remember the proof. Okay, so let's see. Suppose that U is not invertible. So U is not invertible. Okay, so we'll have U say alpha getting mapped to say beta, and U of alpha prime is also getting mapped to not alpha prime, let's say alpha 1, and alpha 2 say also gets mapped to beta, right? Because like there has to be some collision, otherwise you should be able to invert it. It's the same space. And now it's sort of clear, right, that since these are the same, you can write U alpha 1 minus U alpha 2 is the same as 0. And this is basically saying that actually it's even more clear, but okay, so let's call this say beta 1 and beta 2, right? So beta 1 would have to be equal to beta 2 at in some sense, right? Because you're not, yeah, I'm not making the argument very clearly. Okay. So here already the point is that this was supposed to be mapped to a basis, right? So it was supposed to be mapped to beta 1, this was supposed to be mapped to beta 2, and two basis elements cannot be identical, right? Otherwise they're linearly dependent. This just shows that they're linearly dependent. This is probably not the full proof. You have to do it more carefully. I can tell you afterwards how to do it, but that's roughly the idea. That if it's not an invertible operator, it cannot be 1-1. Then something has to go wrong, and then you take those two elements that are being mapped to the same object, and that would tell you that you have linear dependence on what was supposed to be. Okay. There may be other ways of proving it as well. Okay. All right. Any other questions? Okay, let's move on then. So, okay, so I think we would now summarize our discussion so far. So theorem 14 is basically doing exactly that. So it's saying suppose V is a finite dimensional vector space, right, over the field F, and B and B prime are ordered bases, right? And suppose T is a linear operator on V. So it's going from V to V. B is alpha 1 to alpha n, and B prime is alpha 1 prime to alpha n prime, right? Okay. And now it's saying suppose P is the n cross n matrix with columns Pj given as follows, right? So P is this matrix, so alpha 1 prime in the basis B, alpha 2 prime in the basis B, and so on, right? Okay. And okay, so alternatively, oh sorry, so if you have this matrix P, then the matrix for the operator T in basis B prime is going to be related to the matrix of the operator T in basis B via this similarity transform, which is P inverse P. Okay, we just proved this a minute ago. You remember, right? We just went through the. No, is it okay? Yes or no? I don't know. It's not clear? Okay. So here what we are saying is that suppose there's some linear operator T, right? It's going from V to V. And the question we're asking is, we have two different bases. Okay, so we have B and B prime. So we have B and B prime. There are two different bases. We're asking, how does the matrix representation of T relative to B compared to the matrix representation of T relative to B prime? Is the question clear? Okay, and what we did was just a few minutes ago, we proved that the relation is very simple. The relation is just this. So there is some matrix P, okay, that will give you so if you conjugate by it, so if you do P inverse T of P, you will get T in the new base, P prime. Okay, and now you can ask, what is this matrix P? You didn't tell me what the matrix P is. This matrix P is basically exactly the matrix that relates the basis B with the basis B prime. Okay, this we already studied. We said that if two bases are related, if the same space has two different bases, then to go from one basis to the other, there exists some invertible matrix P. So it is exactly the same matrix that appears here. Is that okay? Making sense? Okay. Any questions about the theorem statements? Okay.
So the way that is that like he's a computer and it's a B, so like it takes alpha and B and asks it to beta and B. So it was like some other things we are using. So we are using the not that will do the same pattern in the field. So
Those are vector spaces, first of all. They're not fields, V and W. So you have to be careful. So here we are looking at the same vector space V. We're not looking at different vector spaces. So you have to be careful.
Yeah, so like V is master V, which also vector A. Then the field is in the vector space V itself.
Yes.
We want to convert the V in such a manner that it will be the same kind of mapping in the vector space W.
No, that's not correct. It is the same vector space. You're not changing the vector space. You're just changing the basis. So B and B prime are different bases for the same vector space.
That correspond to the basis.
There's one vector space. Both of them are the same, right?
But it is also that corresponding to basis.
Okay, we'll talk afterwards. Okay, as far as the statement is concerned, you have the same vector space and you're looking at two different bases, and you're just asking, because the matrix for a linear operator depends on the basis, you're asking, how does this matrix change if I change the basis? That is all. Yeah. All right. So, okay, any other questions? We can discuss afterwards, okay? If you still have more questions, because I don't want to waste everyone's time with like one specific thing. Okay. Okay. So let's continue then. Great. So the next part is what I sort of already alluded to, which is the definition of a similarity transformation. Okay, so let A and B be n cross n square matrices over the field F. And we say that B is similar to A over the field F if there is an invertible matrix n cross n, invertible n cross n matrix P over the field F such that B is the same as P inverse AP. Okay, so you have a matrix. So let me say it again. So A and B, n cross n matrices. We say that A is similar to B if there exists an invertible matrix P such that B is the same as P inverse A. Is the statement clear? Okay, so using this language, what can you say about TB and TB prime?
Yes.
Yeah. Is it clear? So TB. Anyone else? what can you say? So given what we've studied so far, so TB is the same as we had in the theorem. Okay? So theorem 14 is what it is. I'm asking, given the definition of similarity and given this equation, can you say something about TB and the relation between TB and TB prime? TB and TB prime. Mhm. Okay, the question is the following. So we are saying let TB and TB prime be as in theorem 14, right? So TB prime is clear, right? It's the representation of the matrix or the linear operator T in the basis B prime. TB is the representation in the basis B. Okay. And I'm asking how are these two related, given that you understand the definition of a matrix being similar to another matrix. They're similar. Yeah. It's a very dumb thing. I'm just making sure that the syntax is getting clear. Is that okay? Okay. All right. So now let's look at an example. So example 16 says the following. It says let T be actually maybe before we move on, can I have a show of hands for those who are still following? Okay, can I have a show of hands for those who fell behind somewhere? Okay, can you tell me where you fell behind? What part were you? Is the okay? So let me ask: is the statement of theorem 14 clear? It's not clear. Uh, let's see. The statement of theorem 13, was this clear? Where we were saying that the composition is just the product. You were with us until then? Was theorem 13 okay for everyone? Yeah, of course the ones following or following not following. So he's asking the ones who fell behind. Was this okay for you guys? Theorem 13? No? Theorem 13 was basically, yeah, I mean, you guys have to stop me, okay? Next time, if the theorem is not clear, don't let me move on because otherwise it will accumulate, right? Like all of these things accumulate, then it is very difficult to catch up afterwards. Okay, so theorem 13, what I'm going to do is I'm going to go through the statement again, make sure that the statement is clear. Okay, the proof you can go back and take a look. You probably understood part of the proof. So the statement is as follows. So the statement is, suppose you have a linear operator T that's going from V to W, a linear operator U that's going from W to Z. Okay. You remember the definition, I hope, of having, so given a linear operator T, we just define what it means to have the matrix corresponding to T relative to some basis BB prime. This is fine, right? Because this was just, you have T alpha J and then you write it as A J I alpha prime I, right? And so this thing is the matrix. Okay. So that is what this notation means. Is that clear? Who else wasn't following actually? I'm just repeating it for your benefit. Can I have a show of hands for those who fell behind? So you guys in there, who else is there? There were a bunch of people over here. Are you guys following along? Yes. You guys have to tell me how else did I know that? Okay, good. So theorem 13. Okay, so I'm just doing the definition, the statement of theorem 13 again. Okay, so we at least have the statement clear. So to even write the statement, we have to understand what it means to have a matrix for a linear operator. Okay? So the matrix for a linear operator T relative to a basis BB prime. So suppose that T is going from V to W. Suppose B is the basis. So let's call it alpha 1 to alpha m, whatever. And V prime is the basis for W. So let's call it alpha prime 1 to alpha prime n. Okay. So the matrix for T relative to B prime is going to be given by Aij. What is Aij? Aij is that you take the linear operator T, apply it to the basis element of B, okay? And you will get a linear combination of basis elements in B prime by definition. It cannot be anything else. And you write down the coefficients. So for each J, you would have a bunch of coefficients, right? So you're just calling them AJI. Okay, and this is what is the matrix representation for T relative to B prime. Is that okay? Okay. So now, suppose this matrix is called A, okay, and the matrix for U is called B. Yeah, we can do that. Now the question is, if I compose, if I apply T first and then apply U, right? The question is, what is the matrix for this? Okay. So what should I write here? So I wrote T B prime, U B prime, B double prime. What do I write for UT? Where do I put the primes? B double prime, right? Okay, so this is clear. So the question is, how is this object related to A and B? That is all the theorem is saying. Okay, so if this is matrix C, then the theorem is asking how is C related to A and B? And the answer is it's just the same. So UT, so B times A. That's it. That is all the theorem is saying. Is the statement clear for everyone? Okay. So that was theorem 13, and the theorem that we just looked at now is saying something. Okay, so let me say the statement, the theorem statement again. So in the previous result, we were looking at two different linear operators, right? And we were asking how do their matrices relate. Now we're going to ask, given a fixed linear operator, but two distinct bases for the same space. Okay, so you have the same linear operator T, which is going from V to V. Okay, and for V, you have two bases. So B is a basis and B prime is a basis. Okay, with the same vector space. And now your question is, how is the representation of T relative to B related to the representation of T relative to B prime? Is the question clear? No, the question is not clear. It is, right? Okay. And the answer that the theorem gives is that it is related by this matrix P. So there's an invertible matrix that is going to give you a relation between the representation in B and the representation in B prime. And the relation is going to be P inverse, the representation in B times P. Okay. And then you can ask, what is P? I didn't tell you what P is. The theorem actually also tells you what P is. Okay. So P is okay, so P is exactly this matrix. Okay, so you write the basis elements of B prime in the basis B. Okay, so alpha, so this is just alpha 1 prime, alpha prime n, say for example. Okay, and this is alpha 1 to alpha n. Okay, so alpha 1 prime is the column, right, for the basis element alpha 1 prime in the basis B. Is that okay? So you can use that to construct a matrix, right? So you can use those columns and you can construct an n cross n matrix. Correct? So you get a matrix like this. Is that okay? All right. So if you get a matrix like this, then it's exactly this matrix that would form P. Is that okay? Is the theorem statement okay? You can go back and look at the proof again if something's not clear. Everyone, the statement of the theorem is okay? Hello. Okay. So then we looked at the definition. Okay, so now we're all caught up. So we looked at the definition of what it means to have a similarity transformation. So B is so we say A and B are similar to each other if there exists an invertible matrix P such that B is the same as P inverse AP. Okay, this is just a definition. Okay, and now just for your own understanding, given this, can you say how TB and TB prime are related? Is it clear how they're related? Does it make sense? If it's not clear, if this is not clear, ask me, okay? This should be absolutely clear. It's a very simple statement. It is just making sure you're comfortable with the language being used. Okay. All right. All right, so then let's continue then. So example 16 is saying the following. So it says, let T be the linear operator R2 defined by T x1, x2 as x1, comma 0. Okay, so this is one specific linear operator that just removes x2. I think we already saw this. Okay. So in example 14, we saw that the matrix for this linear operator T in the standard basis, which is 1, 0, 0, 1, right? This is the standard basis. This is what it was. Right? This we already saw in the previous example. Okay, so now the question is, suppose B prime is the ordered basis for R2 consisting of vectors epsilon 1 prime and epsilon 2 prime as such. Okay, so what we are doing now is B prime is 1, 1 and 2, 1. So we're choosing a different basis, right? We're just going to apply that idea. And so the matrix P, remember the matrix P was what? You write epsilon 1 prime in the original basis, and you write epsilon 2 prime in the original basis, and you make columns out of them. Correct? So let's do that. So what would be the column corresponding to epsilon 1 prime? It's 1, 1. Right? And the column for the other one would be 2, 1. Right? Okay. So one can do a quick computation and check that this is P inverse. Because I'm not doing the computation here. This you've done in like your first chapter, so you know you're very well aware of how to do this. So this is P inverse, and so therefore it turns out that we can use our theorem, right? So we know the representation of T relative to B, and we know the matrix P inverse, and we know the matrix P. Yeah. So we can use our theorem above to obtain the representation of T relative to B prime by plugging in these three matrices and doing the matrix multiplication. Yeah. So one can do this computation. Is it okay so far? And so then this is the answer you would get. Okay. Now we can also compute because it's a very simple linear operator, we can try to compute the matrix directly for the basis B prime using the definition, right? So the definition was you apply it in so epsilon J prime is going to be sum over, let's say A prime, J I, epsilon prime, right? So we can compute this matrix A prime as well. Right, so let's do that. So, okay, so T acting on epsilon 1 prime would be what? Yeah, so let's do that computation. So T epsilon 1 prime was, what was epsilon 1 prime equals? Epsilon 1 prime? One, right? And what does T do? It removes the second component, correct? So this would be 1, 0, okay. And this we want to express as a linear combination of epsilon 1 prime and epsilon 2 prime. So we want this to be, some coefficient say C1 or 1, 1 plus C2 or 2, 1. We want some linear combination. What would this linear combination be? So we can use this. Right, so it cancels the bottom part and it gives you 1 on the top part. Right? Okay, so you can do a similar computation for 2, 0 and you will get -2 and 2. Okay, so how do we read the matrix from this? The matrix, remember, was the rows and columns are getting swapped, right? So we had -1, 1, right? So this will give you the first, and the next one is -2, 2. Right? So this is the matrix of T relative to B prime that we directly computed. Okay, and does it match? It does. Right? So the theorem is fine. It's just an illustration of what's happening. Okay? All right. Ooh, did we finish? Wow. That's it. Which theorem were we looking at? Yeah, we were looking at theorem 16. Okay, so this is done, right? Right. Okay, so now let's look at a more interesting example. So we look at example. Okay, give me a second. Okay, let me see how much we need to cover, and maybe we can skip a theorem. Okay, so we're not going to cover section 3.5 linear functions. Okay, there's some very beautiful theory over here, but I'll probably give it in some assignment questions. Okay, so we only have we have example 17 onwards to cover. That is all we have to do. So maybe what I can do is I can come back to the example in a bit, or let's just do the example. Let's do the example. All right. So let V Okay, so far we saw a very simple example, right? Like we just removed one component, that was the linear operator. But let's look at something more interesting now. So let V be the space of polynomial functions from real numbers to real numbers that have degree at most 3. So that is, so V is poly of degree at most 3. Right? Okay. Now in example 15, we already saw, right, that D is the differentiation operator. So D is the differentiation operator, and B was defined to be, you remember, Fi of X was defined to be X of I minus 1. Right? So we had F1 to F4, and this formed a basis. F1 to F4. Okay, so you have the operator here D, which is going from V to V, and you have the basis B, right? Okay. So now we're going to consider a slightly different basis, right? So we have an operator, we have a basis. To illustrate the point, we are going to construct another basis B prime. Okay, and then we'll do the same exercise. We'll try to see how D can be expressed in the basis B and the basis B prime and how they relate. So we're going to play the same game. Okay, so it says let T be a real number, okay, and define Gi X to be X plus T to the I minus 1. Okay, so instead of X to the I minus 1, we have X plus T to the I minus 1. Is that okay? All right. Now one can check. So what would G1 be? G1 is 1, right? And in terms of Fs, this would be F1, right? There's nothing complicated here. All right. How about G2? So G2X is X plus T, right? Which is what? Right. So T times 1, which is F1 plus F2. Is this clear? Right, it's very straightforward. I'm just doing substitution. So one can proceed like this, and one can write down the entire expression. Okay. Now using this, right, as usual, we can treat the rows as columns. So the first one is this, right? The second one is T1 and zeros, right? The third one is T square to T and 1. So T square to T and 1 and so on, right? So the matrix is fine. And one can also invert it. This I'm not going to do, but we can just assume that you can do this and you can check that it actually works. And we already computed the matrix for the operator D relative to the basis B. This we already did in the previous exam. Okay, so this is what you get. And now what we're going to do is we're going to compute D in the basis B prime using our formula from the theorem. Right? So the theorem statement, when you apply it, it's just a matrix multiplication, and in the end, what you get is very interesting. You get that the matrix is exactly the same as it was. Okay? So even though you've changed the basis, the operator looks exactly the same in terms of the matrix explanation. Okay? Why is it not a linear operator? What do you think is going wrong? Yeah. You're right that it's not like it is singular in the sense that there are non-zero vectors that descend into zero vectors. That is correct. Yeah, it is a linear option. Any other questions? Yeah. Okay. All right. So right. Okay. So then one can check that D is basically represented by the same matrix. It doesn't matter whether you're looking at the basis B or B prime. Okay. And one can also check this much more directly, right? One can just compute D of G1, D of G2, D of G3, and just see that this is the matrix representation. Right? This is the direct computation path, right? That you look at the action of the linear operator in basis B prime direction, right? And so you get this exact same matrix. Okay, because this is the first row, which is zeros. This is the second row, which is 1 0. This is the third one, which is 0 0. Okay. Yeah, that we did not prove. You're right. We just assume that it's a basis. I'll give this as a homework exercise. If it isn't. But it's not too difficult to see because you see that you basically are getting higher powers, right? So G4 has a x to the 4 coefficient. None of the other ones do. So you would not be able to span without the previous one. So sort of. Is that okay? Okay, so the question was, we did not prove that G1 to G4 is actually a basis. Okay? And that is not too difficult to see because G4 is like degree 3, G3 is degree 2, and so on. So you cannot have, they're essentially linearly independent. That is not too difficult. Okay. And they obviously span the space because once you have all the x's, then you can span all the colors. Okay. So now what we're going to do is, okay, so given the matrix of a linear operator in some ordered basis B, one can find the thing in some other basis B frame using the invertible matrix P. It says, however, sometimes it may be much simpler to use its definition directly. And motivated by our discussion so far, we define the notion of similarity. Because I think I messed up. I already introduced the notion of similarity. Sorry, so ignore this part. We already. Okay. Okay. Now, if V is, I think this is like probably the closing remarks for the chapter. So, okay, so if V is an, sorry, for the section, if V is an n-dimensional vector space over the field F, right, and B prime are two ordered bases for V. Okay, so V is going from, yeah, sorry, so V is an n-dimensional vector space over the field F. Tell me. Oh, okay. Yeah, B prime are two bases, right? Bases. Okay. Then for each operator T on V, so from V to T, the matrix B, T B is similar, like this we just saw, to A of T B. Yeah. Okay. So this much we already saw. It turns out it also happens the other way, right? So one can ask, okay, suppose I have matrix A. So suppose for some basis, I have the representation of the linear operator as some matrix. Okay? So suppose I have T, and suppose I construct using some invertible matrix this object P inverse AP. Okay. Now you can ask, does there exist some basis such that in that basis, this is what the linear operator would be? It's a reasonable thing to ask. And so this is what we are trying to argue here. So it says, suppose A and B are n cross n matrices such that B is similar to A. Okay? And let B be any n-dimensional space over F, and B be an ordered basis for V. Okay, so this is precisely the same premise we had. V is an n-dimensional space, but we have only one basis of F. Okay, and let T be the linear operator on V, which is represented in the basis B by A. So basically, it's just saying A is the same as T on B. Right, so we have some basis, some T, and it's saying that B is related to A by some linearity, similarity transformation. Right. So now, if B is equal to P inverse AP, one can let B prime be the ordered basis for V obtained by B using P. So one can just define alpha J prime to be the basis that is obtained by multiplying with P the basis alpha. Okay, so one can just use this definition. Okay, is it making sense? Oh no, did I lose you guys? Is it fine? Are you following? Yeah. Okay. So you just define the basis directly like this, and it turns out that the ordered basis, T in the ordered basis B prime would actually be P. Okay, this you can just do a direct computation and you'll find it. Okay, so the correspondence is quite direct. And what else does it say? Okay, so thus the statement that B is similar to A means that on each n-dimensional space over F, the matrices A and B represent the same linear transformation into possibly different order bases. Okay. So, yeah, a priori, this is not clear at all, right? So if I give you two matrices and you find that they are somehow related by this P inverse thing, it's not clear what this is actually doing. But now this gives you a very nice way of conceptually understanding what is happening. It is saying it's this exact same linear operator, right? Just that it is written relative to different bases. That is it. Okay, so it basically unifies a lot of seemingly different looking matrices. Okay. Okay. So similarity, so okay, one can check that similarity is actually an equivalence relation. So one can check that A is similar to itself, so one can use P's identity. If A is similar to B, using say P, then B is similar to A, right? So yeah, so let's do the first step. So A is similar to itself. So we want to show that A is similar to itself. So we have to use some P, right, such that P inverse AP is the same as A. So what P can we use here? Yeah, so you basically take P to be identity, right? This will give you what you want, right? So it shows that A is similar to itself. Is that okay? Okay. Now we want to show that A is similar to B. So A is similar to B. Sorry, given that A is similar to B, we want to argue that B is similar to A. How will we do this? Any ideas? Exactly. Exactly. Anyone else? How do you want to do it? So suppose that, so this means what? It means that A is the same as P inverse BP, right? Where P is invertible. Okay. Now I want to argue that B is similar to A. How would I do it? Is that reasonable? Right? So you basically get if I multiply by P on the right hand side, and I get this object. Is that okay? Is that correct? Hope I didn't get it from here. Okay, so what does this show? This shows that if A is similar to B, then B is similar to A. This is fine. Okay. And what is the last step? The last step is saying if A is similar to B, okay, and B is similar to C, it's claiming that A is similar to C. Because how do we see this? So A is similar to B, we can write it as what? P inverse BP. This is fine. Right? And then B we can write as say P bar inverse, yeah, P bar inverse B. Let's call it Q actually, it's easier. Oh, sorry, C. Is that okay? Okay. So now we want to argue that A is similar to C. So we want to argue that there exists some, I don't know, E such that A is the same as E inverse C. Right? So how do you find E? You can just substitute, right? Any ideas? Right. Okay. And now you can read the matrix. Correct? Simple enough. Okay, so now we've looked at all the properties that you need for something to be an equivalence relation. We've checked it's reflexive, we've checked it's transitive, and what is the other one? Oh yeah, it's symmetric. Yeah, that's the other one. This one is symmetric, right? This one is reflexive. Reflexive is to itself. Symmetric is AB is the same as BA, right? And the last one is transitive. Right? Okay. Okay, and so this part is fine. These last two things I will leave as exercise. Okay, so the claim is that the only matrix that is similar to identity is itself. There is no other matrix that can be similar to identity. Okay, and why that is basically regardless of which P you use, P inverse P would be identity. So identity will not be. And the only matrix similar to the zero matrix is again the zero matrix. So exactly the same. Okay, regardless of which P you use, you can get P. Okay, fantastic. So we have 5 minutes left. Okay, so I think we have two options. I'll at least give you the definition of linear functions, okay? Because this is good to know. This is not going to be in your exam, so you can look at it at leisure later. But okay, so the definition of a linear function is very sweet actually. It just says that if V is a vector space over F, okay, and a linear transformation is defined from the vector space V to the scalar field F, then this thing is also called a linear function. Okay, so we've considered linear transformation, right? So we've looked at T that goes from V to W, where V and W are vector spaces. The point is that if W is a field, okay, so V is over some field, right? Over some field, right? So now instead of going from V to W, if you take W to just be the field itself, which is like the most trivial vector space there is, then this T is going to be called a linear function. Is the definition okay? All right. And if you want to write it down explicitly, it's just saying that, this object f is going from V to W, and it satisfies the relation for a linear function, or so a linear transformation. Right? That linear combinations go to linear combinations. Right? Okay. So here are some very quick examples of what linear transformations are. So one very easy example is that you basically take multiply by scalars and you add them. Okay. So this might look very similar to your inner products, right, that you have seen, that you're multiplying on the left-hand side with some vector, and then you get the inner product. Right? This you've seen in physics and so on. So taking the inner product is basically a linear function. Okay, so that is one. The other one is the trace, right? This everyone has seen. Trace is you just sum the diagonal entries in matrix, and it's a very fundamental object. We'll see. What is it doing? It's taking the vector and mapping it to a scalar. Okay? So this is also a linear function. And then there's one about integration that we'll not quite too much. Okay. So now here's a very nice claim. So the claim says that if V is a vector space, then the collection of all linear functionals on this vector space V itself forms a vector space. Okay. And this vector space is given by LBF. This should not come as a surprise because we already saw, right, that the space of all linear transformations form a vector space. So if you have a special case, obviously it would still be a vector space. But it actually has a name. It has an important name, and it's called the dual space of the vector space. And it's denoted by V star. Okay. Now it turns out that using our results so far, you can show that the dimension of this vector space matches exactly the dimension of the vector space you started with. So the dimension of the dual space, okay, is exactly the same as the dimension of the vector space you started with. The dual space is just a set of linear functions that are in the dual space. Okay. Further, it turns out that you can also define a basis as follows. Okay, so this Fi, so basically you're sending alpha j to delta ij. And this is the map. So you take a vector. Okay, so the ith linear function, what it does is it takes any of the vectors, and if it matches exactly the vector it's looking for, it gives you 1. Otherwise, it gives you 0 in the basis. Okay, so this is very much like when you're doing your orthogonal vectors, right? So if you have, say, this is V1, this is V2. Starting to use sorry. This is vector 1, this is vector 2. We know that vector 2 dot vector 1 is 0, and vector 2 dot vector 2 is 1. Okay? So it is basically generalizing that idea. Okay, so it's saying that there is some linear function, and it will give you 1 exactly for one vector and 0 otherwise. And it turns out that this thing actually spans the set of all linear functions. If you look at all the f1s to fn's, it spans the set of all linear functions. And there's n many, right? Because we already said that is the dimension. So f1 to fn is is a basis for V star, and this is called the dual basis. Okay, there's just some words that you should know so that later when you see, you're not completely lost, so you know where to look. Okay. So I guess we can stop here. Next time we start axioms, and we look at eigenvectors and Thank you so much.